This is Rust from Go's perspective, or Rust for Gophers. And my goal with this talk is hopefully to help anyone who is either learning Go or is already a Go programmer in your endeavors to learn about Rust, kind of what makes it tick, and what it looks like to sort of apply some of the common patterns in Go to Rust. These are two languages that have come up kind of around the same time and have some overlap in terms of who tends to be the programmers who work in these spaces, as well as the problems they solve. With that said, I hope that this talk and kind of the general thought experiment of looking at one language from the perception of another can be a source of unity for these programming communities. In doing the research for this talk, I found a lot of noise and a lot of people shooting past each other and being snarky and mean and everything, which is all just to say if you're a Go programmer and you're learning about Rust, or you're a Rust programmer and you're learning about Go, just be nice, be inclusive. So, about myself, my name is Damien. I'm at Damien Stanton on Twitter and GitHub and elsewhere. I'm a senior machine learning engineer at SignalFrame. We're an IoT analytics startup here in DC. If you're not familiar with ML engineering kind of as a discipline, it's an interesting blend of systems programming, distributed systems engineering, and data science. And what that really means is that I wear a lot of hats, and I've had to work in a lot of different programming platforms and languages, including Go, Scala, and Rust. I've been in the Go community for a while, since about 2014, and I started learning Rust around the same time, although my Rust work has really been more for hobby and for open source. In my opinion, I think Rust is the future of systems programming. And when I say that, I really think Rust has a lot of features that make it a true sort of heir to C and C++ in a lot of problem domains. And when I talk about kind of the way Rust's memory model works and how it sort of contrasts to Go's, I think that will make sense. So, what is Rust? This is a very strange thing to be saying at a Go meetup. But Rust is a language empowering everyone to build reliable and efficient software. That's sort of the official slogan on the Rust Lang website. I like that because it's not overtly technical. I think it used to be something like Rust is a systems programming language that is blazing fast and prevents site faults and data races and everything, which is true and is interesting from a technical standpoint. But I think this captures kind of the ethos of what the whole point is that the Go community does very well, which is to say, if you pick up this language, you'll be able to build tools and systems that scale and that are reliable. So to kind of go through a short feature list that Rust shares with Go, just like Go, it produces native cross-platform binaries. Just like Go, it's statically typed. And just like Go, it's designed for writing concurrency-safe and memory-safe code. Although that third point, the manner in which Rust does this is very different from Go's. We'll see a little bit about that. Some differentiators for Rust, it has first-class WebAssembly support. I should say, for all these slides, there's tons of links and references here. This link is a quote to one of the creators of Docker, who said, if WebAssembly and another technology piece called WASI existed in 2008, Docker wouldn't exist at all. The WebAssembly is very important because it's a runtime that can run natively in the web browser and in the future, potentially other places. So that's interesting. Go does have experimental WebAssembly support, but Rust is a first-class citizen, so to speak, in the WebAssembly world. Another thing that's unique about Rust is that it does not have a runtime. This has implications when it comes to doing things like reflection and understanding Rust's unique memory model explains how it works without a runtime, as well as not having a garbage collector. And that will make sense when we actually start looking at it. And then another differentiator from Rust and any other language is that its type system is pretty unique, and it has a pretty powerful macro system. And we're not going to delve too much into, we're not going to delve actually at all into the type system, and we're not really going to cover macros that much, but it's good to know. So if you're a new Rust programmer and you want to see what third-party packages are out there, the place where this is published is crates.io. Now, if you're a Java developer, crates.io is pretty similar to the Maven Central repository. Crates are where public Publicly sourced Rust code is sent and packaged. And if you look at any particular crate, you'll find tons of information about it, as well as statistics and stuff like that. Likewise, for documentation, there's a documentation system, docs.rs. This is all automatically generated from the publicly sourced crates, and this is all very similar to what you'd find in GoDoc. When you publish something on crates, your docs are automatically built. So, we'll start with the Rust build system and its tools. So, Rust has what they refer to as a tool chain, and there are basically two programs that you use most often to interact with Rust programs. One is RustUp, and the other is Cargo. So, I will show you briefly what these things do. So, RustUp is essentially a version management tool. So RustUp allows you to install different versions of the Rust compiler on your system side by side. It also allows you to add new compilation targets. So for example, I have wasm32 unknown, which means when I write Rust code, I can tell the Rust compiler, I want you to compile my program for WebAssembly, for example. This is really important when it comes to using an unstable or feature preview version of Rust, because you can just run it alongside your existing version of Rust. And the other tool that's most commonly used is Cargo. Now, Cargo is Rust's, that's a little too big. Cargo is Rust's build tool. Now, this is equivalent to the Go command, essentially. Cargo underneath the hood calls the Rust C compiler, the Rust documentation generator, and other binaries. That's not important. Essentially, you use Cargo to build new projects, to run programs, and to do other things like run third-party linters and other things over your code. So what this looks like in practice, like we said, Cargo new world, create a new program. Now we have a Rust program. So if you look at the main, this is very straightforward. One thing you might notice is println here has an exclamation point at the end. In Rust, any function invocation that ends with an exclamation point is a macro. And it's not too important to discuss macros that much in depth in this context, because we're talking about, okay, well, how do I print to the screen the way I would do function print line, right? Macros are essentially a different way to have functions accept variadic arguments, because in Rust you cannot have, say, like a list of strings. Or no, I shouldn't say that. It's not that you can't have a list, but you can't have an unknown number of strings. In Rust, functions have to have a known number of arguments. So macros do a couple things. One, they allow you to have variadic functionality. And then macros also are useful for sort of transforming Rust code. And this is more akin to the traditional concept of macros that you might be familiar with from C or C++. So I just built this program, and if I want to run it, I can just say cargo run, and it runs. Now, probably familiar with the dep tool for Go. Dependency management in Rust is managed through the cargo.toml file. And so if I had dependencies here, I would add them. If I had build dependencies and so on, and there's tons of configuration options to allow you to build programs as you need. That. Now, another aspect of the build tooling that is very important is testing, right? So it's sort of a Go convention that whenever you write any code, you write the unit tests alongside it. So this concept exists in Rust as well. So if we were to create a new project, and in this case, I want to create a new crate. So I'm calling cargo new with this lib flag, and I want to call it my lib. Now, if I look at this, we'll see something different here. Now, the body of this library would be written up here somewhere. And what you see here is the test module. Now, when you look at the code repository for this talk, in the main binaries for all the examples I'm going to walk through in the Rust playground, you'll actually see unit tests that sort of assert the correct functionality of those things. So in Rust, unlike in Go, and unlike in many other programming languages, unit tests live in the exact same place as the main functionality. So you can unit test on a main.rs, and you can unit test in any module that you're building. So this test just asserts that 2 plus 2 is 4, and that test works. One last piece of functionality that I want to cover in terms of cargo is, let's say I have some function. Well, bear with me one moment while I write it out. So Rust, like Java, for example, has visibility modifiers. So when it comes to, and I'm covering documentation here, so if this is a local function, it will not be documented. If I add pub, then this will signal to the Rust doc program that this should be something that is documented. So I'll say simple addition file. Now, one thing that's unique about Rust's doc annotation in terms of the source code is you can add markdown here. So let's say here is an example. I can type. Anything in a code test here will be executed. We can say use, I call this mylib. Okay, so the doc test worked. Now if I run this, what you can see here is automatically built documentation for this. The stuff that I wrote in Markdown is automatically rendered to HTML here. And this is really useful because you can actually do anything you would do in Markdown in documentation directly. This is awesome for being able to include diagrams, and you can do referential links inside the documentation to say like, okay, well, you're supposed to be using this data structure, so you just click the name and you'll automatically be taken to the right place. And the other thing that I should add is that this test is part of the test suite. So this is considered a doc test, which you might be familiar with from Python or Haskell. And these tests are automatically compiled. You would have to add a directive into the little code fence to say, don't run this in order for it to not be included as part of the tests. So that is all I wanted to cover as far as the tooling. Okay. Now, the sort of the meat of this talk is I'm basically going to go through and show some very toyish examples in Go that kind of walk through the basics of, okay, how do you write functions? What are the types like a little bit? How do you add methods to a data structure? People asked a lot of questions when I was doing research for this talk on what is the difference between a Go interface and a Rust trait, for example. So we'll look at all those things a little bit. So the first thing I'm going to cover is just a simple function that doesn't make any sense because all it does is take a string and it returns the length of that string. Now in Go, obviously, we would define a function that does these things. It's all kind of par for the course for a basic function. So let's see how we would do this in this. So let's say that one is called flow. And I'm not going to cover some of the very minor syntactic differences, like the fact that Rust does require semicolons, unlike Go. Basically, all that. iSize is Rust's type that's similar to int. And just like in Go, there's different variants. You can have I8, I16, I32, and so on, depending on what size you need. So what we're returning this type assertion and type coercion in Rust is done with the as keyword. The length of a string in Rust returns an unsigned integer. So we do this coercion so that we get the same signature that we wanted in Go. So we save this. Nothing works. Now, why does this happen? Oops. First thing is I wrote it like it was a Go program. That's not going to work. Okay, mismatched types. We expected a string, and we found this other thing, an ampersand stir, which seems a little weird, right? This looks like a string. So what's the deal here? The compiler provides a helpful message. It says, okay, convert S1 to string, which seems a little awkward, but we'll see if it does the trick. Okay, that returns 5. This is what we wanted. In Rust, there's a couple different ways to sort of turn one type into another. And I'm not talking about type coercion like this, but in terms of providing a method that knows how to turn itself into another type. And that concept will make more sense when we talk about traits. But I find doing it in the postfix like this, like saying S1 string dot to string, just feels awkward. So what I prefer to do is go the other way around and say, okay, well, I know I want a string, not a whatever stir, and say string from. Okay, and we get the same thing. So that'll make sense. Now, let's say we wanted to change this S1 variable. We're doing something in our program, and we want to say comma gophers. Okay. So let's see how that works. Okay, this doesn't work. The error message here says cannot borrow S1 as mutable as it is not declared as cannot borrow S1 as mutable as it is not declared as mutable. So this is a core feature of the way Rust works in terms of protecting unexpected mutation of data. All variables in Rust are immutable unless specifically specified as mutable. So let's see if we can correct that error. Okay, so we told the compiler you need to be able to change S1. Now here's something interesting. We get another error, borrow of moved value S1. Now this is weird, right? Move occurs because S1 has type string, which does not connect the copy trait. Well, that doesn't really make any sense. Value borrowed here after move. And this sort of situation is something that people coming to Rust from almost any other language, except certain situations with C++, get really tripped up on, and it's really confusing. Like, what does this mean, value moved? And they didn't do anything with it. And we'll come back to exactly why what I'm about to do fixes the situation. But suffice to say, I put ampersands everywhere. And it works. This is the tried and true thing with pointers from the days of C to Go to Rust to anywhere you're dealing with pointers, right? Just try asterisks and try ampersands until it works. So, what is going on here? So, a tale of two strings, right? So string and stir must be different somehow. And it's interesting that this is like the most common problem that people run into, and it makes sense because when you're programming, you're almost always dealing with some string somewhere. People get tripped up on this, but if you actually dive down the rabbit hole and try to understand like why are strings and stirs different, you sort of are forced to learn about the whole Rust memory model and what the concept of ownership and scoping actually means. So I'm going to start with the technical answer. So the reason this this is different and one worked and the other didn't. Strings are what's called an owned type in Rust. Strs, on the other hand, are string slices. Now, slices in Rust are pretty similar to slices in Go. They have some sort of fixed array backing underneath, and you can do things to them and take components of them and whatnot. And so it turns out that string literals in Rust, when you just say hello, colon, semicolon, string literals are a reference to a string slice. They're not a string at all, which might seem odd, but as we go through, it might hopefully start to make sense. So if we look at a diagram of what's actually happening, we're going to see what borrowing and ownership are. And I'll refer back to this a couple times. But essentially, you can understand that S in this case is a pointer to the string type, but it holds nothing except a pointer to that type. So it's literally just a label of some kind that points to the type that actually owns the space in memory. So in this case, S1 would be statically included in the binary that's produced by this program, while S just disappears at some point. And the exact place that S disappears is when this function goes out of scope. And we'll talk about that a little bit. So as I said, this sort of forces you to talk about the memory model. So what is ownership? Basically, ownership is a principle that the Rust compiler and the Rust borrow checker, which is a component in the compiler, use. And ownership has three rules. Every value in Rust has a variable that is its owner. And there can only ever be one owner at a time for that particular thing. And then when the owner goes out of scope, the value will be dropped. We'll talk a little bit about what scope means. So that's one component. The next component is references. So the ampersand that I added to fix the problem means take a reference to that type. So I said take a reference to string. We haven't seen dereference, but essentially it's the opposite. It's the same way you dereference in Go, which is to say follow over to the real thing. Now what's borrowing? So this is the best sort of lay description that I could come up with to describe what borrowing is, and this is largely taken from the Rust book, and there's a couple of other pieces of documentation that help with this. But basically, this is what borrowing is. So I have a function foo, give it a reference to a type, like ampersand my type, and foo returns its value. Its scope is dropped. But what happens is because we passed in a reference, nothing happened to the original value. And so we've sort of passed the rule of the borrow checker, which said this value needs to live longer than the scope of that function. And when I say live, we'll talk about lifetimes a little bit later. And this is why it's called borrowing, because you only gave a reference to a type. You didn't own the type. That's really important. This is kind of the linchpin that holds together Rust's memory model. And it's based on a concept called regional memory, or managing memory by region. And this notion of having variables in your programs only live within a certain scope that's well defined, and have that be the method that determines whether they get allocated or dropped or not, is the way that everything works. And that explains kind of how Rust works without having a runtime like Go, but it also doesn't have a requirement that you manually allocate in free memory like you would in C. There's a link to the paper here, which is called Region-Based Memory Management in Cyclone. Cyclone was sort of a research fork of C or C++ that sort of laid some of the rules that were later incorporated into Rust. So the one concept that I mentioned just now was lifetimes. So what is a lifetime? The way we'll explore a lifetime is to port this simple program into Rust. So we have a couple strings. We want to check whether one is longer than the other. We want to return longer with a 2, and if they're equal, we return something else. There. let's say I'm an astute programmer. I didn't like the fact that I had to keep converting these strings into slice of str, which seemed to be like a more literal representation of what I wanted. So I'm going to say that everything is just a reference to string slice. So let's say. Now we could directly port the branching conditional here in the Go program to say, like, if the lengths are the same, return either. If length A is greater, return A. If nothing else, return B. But one thing I want to show that's an important differentiator in the Rust syntax is something called pattern matching. This would be familiar to you if you've programmed in Scala or Haskell or any other sort of functionally flavored programming language. So we're going to match on A. And essentially the way pattern matching syntax works at Rust is you have potentially a variable here, some sort of condition that's satisfied, a fat arrow, and then the thing you want to return. So in this case, we know that we want to return one of the input parameters, so we don't care about an intermediate value. We just say if A outline is greater than B outline, we return A. And you do almost exactly the same thing for B. And then just a naked underscore is sort of a catch-all condition. You can think of this logically as otherwise. We say either. And let me call this two strings. Let's see what happens. Okay, expected a lifetime parameter. So this is where you'll start to understand why lifetimes are important. So, this is explained a little bit better in the help message. This function's return type contains a borrowed value, but the signature does not say whether it's borrowed from A or B. This is important when you're talking about references in Rust. References always have an implicit lifetime, but the compiler can only understand so much about the intention of your instruction for that lifetime. So in this case, Rust knows that whatever is returned and these parameters that are passed in has to exist for some amount of time. But it could be that A and B have completely different lifetimes. And there's no way for the compiler to tell that. So it requires what's called a lifetime parameter. And this is not something that's really confusing, but it's something that sort of puts people off, especially when they come from a very clean language like Go, because it looks very noisy. There's definitely some additional syntactic element that needs to be added here. And people don't like it, but it's important because you're essentially required to tell the compiler, okay, what is lifetime of this thing? The convention oftentimes in Rust is to make a lifetime parameter be a single letter. But I think in this case, because the parameters are already A and B, this would be especially noisy and confusing. There's nothing wrong with just making it something that is more meaningful to the reader of the code. So we can just say on. And then what I do is I add this lifetime parameter everywhere that these references need it. And now it works. We see that Java is the answer that's output here. So one thing I will mention very briefly, but I won't have time to talk about in detail because it's really, it's important to understanding Rust when you start developing programs, but there isn't a direct analog in Go because Go doesn't have this immutability protection. Essentially, what are called smart pointers in Rust are data structures that are used to increase the flexibility of your control over that ownership and borrowing model that we talked about. Essentially, first off, everything in Rust is allocated on the stack by default. You have to manually box something and tell the Rust compiler, put this on the heap instead. It's not like Java or Go where certain data structures are automatically boxed or auto-boxed. That doesn't happen here. So that's what box is for. These other types, RC, which stands for reference counted, and ARC, which is atomically reference counted, these things basically allow you to simulate as though a piece of data had multiple owners. That's a little bit more advanced and it's not that useful for what we're talking about, so I won't talk about it any more than that. Ref-T and ref-mut-T, basically this is a more complex situation even than the other two, where you have multiple references to a given type and you need to sort of internally mutate that type. There's no way we're going to get anywhere close to that right now. So that's why I just want to gloss over these pretty quickly. But as I mentioned before, these are links. These go to the documentation for these particular data types. That's super helpful in understanding this. So this is kind of the most interesting thing that we've applied at SignalFrame to Go is and we didn't borrow this from Rust, but we sort of had to come up with very similar solutions due to the scale of systems that we're building. People always ask, okay, how do you represent null? And how do you handle errors? So in Rust, these are done with two generic data types. And they're enumerations, which is just, if you're not familiar with an enum in C++ or other languages, essentially an enumeration has to be one of its variants. So if I give you an option, that data type has to be none or it has to be some. Or if you give me a function that returns some result, it has to be either okay or it didn't work. The result pattern is sort of, although it's generic, it's in a way similar to the traditional Go error handling pattern of saying, okay, give me a result and an error, and then if error is not nil, do something, and so on. So this is another piece of Go code that we'll port, and essentially what we're doing is putting together a simple data structure that is a point that has a name and an x and y value. We'll add one method to that data structure. Someone online asked me, what is Go's equivalent of having an optional type? There was an interesting thread on Twitter in the response, but basically there isn't one. But you can sort of mock it if you make your data structure have a field that is a pointer, because you know that if that structure gets initialized without that particular field, then it's nil, and you know how to handle nil. So that's why struct is a pointer here. But we'll see how this is a little bit different in the Rust version. So, first thing, which is interesting to see, is I'm going to right now. Let's just create a data structure and try to print it. That will showcase something else that's unique to Rust called attributes. Now, I mentioned that we want to know whether something can be nulled, so to speak. So in Rust, as I mentioned on the other slide, this is done by optional type. Use the option of that type. Say the same thing as the Go fields. Okay, data structure. Now let's see. Okay, so this is different than Go. We tried to just create a new point, but Rust explicitly disallows sort of naked data structure creation like this. You have to initialize the values. And this, again, has to do with the mutability guarantee. And we can see how we can instruct the compiler to automatically do this for us. But for now, let's just say x is sum of my point. Remember, sum is the required variant of the result type, or sorry, of the option type. Oops. It's 0. Say y is 0 also. Now let's see if this works. Oops. I made the same mistake that we made at the beginning, right? So this has to be string created from this literal. Okay, so this is something else that we haven't seen yet. So point doesn't implement func display. So point cannot be formatted with the default formatter. It's interesting. So this is indicating that our data structure doesn't implement a particular type. So let's see how we'll follow the compiler's instructions and we'll fix this. Okay, point doesn't implement debug. So these are traits that this data structure doesn't have, but the compiler is saying, I think you want this, here's what you need to do it. So we could manually implement a trait, and we'll see how traits are implemented a little bit later. But we can have the compiler intelligently create this trait just based on the data structure, if it's something that has one of these attributes, as they're called. Derive bug. Now the compiler knows how to print our thing. And notice that because we set name to be an optional string, you can see that in the printed value. Name is sum my point. If we had initialized this to be none, it would appear as none. So let's try adding a method to this. Now, in Go, when you add methods to a data structure, you simply pass typically a pointer to that data structure to a function in the function receiver slot, and you just add that functionality, which I think we still have up on the slide, right? So get name in this case takes a pointer to a point structure. We want to check whether the name is nil, and we return a string or error value based on that. So essentially, we want to do the same thing in Rust. Rust methods are not implicitly understood the way they are in Go. In this case, we have to create a specific block of code that is the implementation for point. So we say impl point. And we say get name. Get name in this case takes a reference to the data structure itself. And then remember, we wanted to return a successful string value for the name and an error of some kind. In this case, it's going to be a result of string. Now, what do we return for the error? Well, in Go, we do this through the errors package itself or through some other error mechanism. In Rust, what we'll do here is create a custom error. And we'll do this through an enum. So we'll call it point error. Now we have the signature, and we'll come back to the actual implementation in a second. So what is a point error? Let's say point error. And we're not going to make it very comprehensive because we just want to match the specification of the Go program. So we give it one thing. We say no name. Now this right here is what's known as a tuple structure in Rust. And essentially, this is the same as defining struct up here, except that it only has one argument. And what we'll do is we want to pass in a string literal to make it easier on ourselves. So we'll say reference to a string. But remember, we need a lifetime parameter whenever we're just including a reference like this. So add one. We'll call it PE for point error. Just say that when I create a new point error with whatever message is in their name, that string reference has to live as long as the data structure itself, which makes sense. Then the actual implementation, we can say if self name. Now, when you add an option wrapper around a given type, you'll get convenience methods from the trait implementation that let you sort of ascertain the existence or the correctness of your closed type. And that makes it easier to create correct code in this case. So there's a method called isNone. So if there wasn't anything, then what we want to return is a point error with the broken variant, or with the known variant, and close up set. Otherwise, okay, so we know that name exists, right? So remember, name is an optional type, though. Rust protects optioned types using methods that require you to basically ascertain whether you should be pulling out the value or not. Because we know that name definitely is something, it's not none, we can safely what's called unwrap the type. So we'll create inside the variable, and we'll say this is self name. Well, I'll do it this way to actually show you an error. Yeah, actually, it's a little bit differently. Okay. Well, actually, no. I'll just write that the correct way. So we'll create local variable. I'll explain why I have to add this as ref method in a second. Essentially. Curse of live demos, right? Let's see. I'll cheat. Basically, ignore documentation. But essentially, the way this works is we created this point error with a known invariant. We checked whether name exists or not. And then we say, well, we know that it exists, so we take out a reference to the internal type, and then we unwrap that type and convert it to a string because we know it's safe. The reason this asRef method is required is because option types themselves don't implement what's called copy trait, and that's one of the constraints that Rust puts around what types of values can be copied around, and that's another safety mechanism. So, if I run this one, this is what we would have seen in the playground from the live coding. Essentially, we know that there's some point, we got the construction correct, and we get back some values. Now, one other thing I wanted to mention is there are several of these attributes that can be added. So if, say, there was a requirement that you needed to be able to create sort of a default construction of your particular data type, there is a derivable attribute called default. Then what we can say here is you're telling the compiler to just look at the data structure. We're going to say that it's a point. Right? Look at it, create some sort of default. Okay. And just like in Go, it created some sort of reasonable default value. Name is set to none, x and y are 0. So, another area that people have tons of questions about, okay, how do traits compare or contrast to Go's interfaces? There is a talk by Frances Kenpoy from GopherCon China 2017 called Understanding Interfaces. I highly recommend that talk. It's a really good sort of in-depth discussion of how interfaces really work in Go, and I really like this particular image because it sort of describes interfaces in terms of set semantics, whereas interfaces are these abstract behavioral thingies that exist in some space that is somehow related to Go's concrete types. And I really like this picture because it's just really intuitive, right? So in Go, any data type that implements the required methods of IO writer is an IO writer, and you can pass it as such. Same thing with the union of two different interfaces. It's sort of one of Go's standout features in terms of its design is being able to do this and have flexible sort of behavioral constraints applied to your particular data types. So Rust does something similar. There's too much to type to try to live code this, so I'm not going to do that. But essentially what we're going to look at is, say we had some tweet and we wanted a way to summarize it. So we decided to abstract out the summarization behavior because we're a news media company and we do things with things that aren't tweets. So just like in Go interfaces, Rust traits parameterize behavior instead of a particular data shape. And just like in Go, you can pass in a trait, or I should say, you assign a parameter to be anything that implements a certain trait, just like in Go, how you can pass in an interface. And anything that satisfies that interface is okay as a parameter. So in this way, it's just the same as Go. Now, one differentiator in Rust is traits can have default and self-referential methods. So if we go back to the Go example, I don't know if this is hard to read or not, but summarize author and summarize both have to be implemented for this interface to be satisfied. If you tried to pass in something that only implemented one of them, you would get a compile error. In Rust, it's a little bit different because traits can have default implementations. So we can say if anything gets summarized, refer to the required implementation method, which is summarize author. If you look at the docs for this, you would see the traits attributes, and then there would be two separate headers. One would say required methods, and another one would be provided methods. So in this way, you can really make very comprehensive behavioral constraints and make the code on the user side very easy to use. And when you combine it with Go's generics implementation in the language, you can get something close to Haskell type classes. They're not exactly the same, but essentially you can say, if you have some function, you can define its parameters and its return types with logical constraints about its behavior. And a lot of the traits, a lot of functionality in the Rust core standard libraries and certainly third-party libraries take huge advantage of this. You can have really expansive functionality over things because of the generics that you can't really get with coding in the base in terms of ease of use. So another aspect that people had a lot of questions about was concurrency. This one is a little bit tricky because Rust is going through a pretty major change in terms of the concurrency options in the standard library. I'll show a little bit of kind of Rust's standard threading model, and Rust has an implementation of channels that work very much like Go channels. And I'll talk a little bit about kind of where Rust is heading over the next several months in terms of a much more expansive sort of coroutine runtime, I would say. It's going to allow asynchronous programming that feels much more like linear programming. And that is something that Go developers take for granted. So first off, just simple threads and channels in Rust. So essentially, channels are familiar CSV style channels, as you would see in Go. And in this code, essentially, we just create a channel. A channel has a sender and a receiver. This is not that much different than pushing into a channel and receiving out from that channel in Go. We create some threads, and we create one thread. We send a value onto that thread, and then we read something out of the channel. One thing I didn't mention was closures. Just like in Go, Rust supports anonymous functions, and the syntax for this is two pipes and then some return value. If it were something very simple, you wouldn't need these braces, but it is it's just like it is in Go. You can increase the functionality and sort of interstate management of something by using a closure. But all that is to just say this is a closure. And this move keyword has to do with the ownership requirement. Move basically tells the Rust compiler, use move semantics here to make sure that the closure actually owns the data that it's operating on. This is important because you wouldn't be able to send anything, you wouldn't be able to properly return data if it wasn't moved because it would only exist inside the closure. Then once that closure went out of scope, it would disappear. It would make sense. This example is sort of like a Go routine being spun up, inserting something into a channel, and then we read it back on in the main Go routine. This example is similar. Essentially, this is a fan-in pattern. So, and this is pulled straight from the MPSC channel documentation. Basically, you just create a channel. You, again, ownership comes into play here. You have to clone each of the sending channels. Clone means actually make a copy of the data. So you clone it 10 times. You have these 10 channels. And then you create the threads. You put data inside them. And then we do the same thing on the receiving side. Just like in Go, you can use loops, like for loops or any other sort of iteration construct to drain channels. And there's also convenient methods for this. I think MPSC channel receive has something called try-iter. And if you're not familiar with iterators from, say, Python or some other experience, iterators are essentially a data structure that allows you to take a value and say, give me the next thing, give me the next thing, give me the next thing. So there's a method called try-iter, and that gives you an iterable, and you can say, okay, just pull everything off, give me everything from the channel. So the reason I sort of am quickly going over these channel implementations is that it's pretty close to what you would see in Go. And if you're familiar with Go routines and channels, you would not be confused by anything here. So what about lightweight threads, sort of so-called green threads? Well, back in the early days in 2014, 2015, Rust actually did have something similar to Go routines, some sort of green threading event runtime, but this was dropped. They were just using a traditional threading model. There were two reasons for that. One was that the complexity and overhead of having that runtime included in that early version of Rust wasn't worth it, especially while they were trying to figure out things like implementing the full ownership model correctly and understanding how to do other aspects of concurrency through the channel system. So Rust does not have green threads as of yet. Right now, Rust is moving to have async and await be keywords. This is something that's taken the programming community at large kind of by storm over the last couple of years. JavaScript has async await, C++ has async await, Python has async await, C# has had async await for many, many years. And it's coming to Rust as well. And essentially what this is they've determined the best way to provide sort of a zero-cost runtime for things that are like Go routines. In the Rust nomenclature, they're called tasks. Don't worry about this gnarly-looking trait, but the reason I put this here is that this trait is what allows anything that you mark as a future, that is some value that's going to exist in the future, can be turned into a task that this runtime will then figure out how to run. Now, this is very similar to how the Go routine scheduler kind of works in the runtime on its own and says, okay, this is how this is going to be coordinated, and you'll asynchronously get results as you need them. And then down here in the second example is really just a simple example of, okay, what does this actually look like in action? So async is a keyword. We're saying that this function has some asynchronous components to it. And this would be very familiar if you've used JavaScript in the last couple of years. So we create a stream, and then we await the data, and then we do a couple of assertions to make sure that the data makes sense. I'm not going to walk through this code because it's very much in flux right now. I did provide a couple of examples in the repository, but it's a major change to the concurrency ecosystem. So right now, there's a lot of tooling built around this project called Tokyo. This uses its own features and executor model that sort of does task management, does all the things that the Go routine scheduler does. And right now, Tokyo is being changed to work with the standard library implementation, which is called Futures. And as far as the time scale for this, I think in the beta version of the Rust compiler, async await and futures and everything will be stabilized by the end of this month. And then probably by the end of the year, it's going to be in Rust stable. So if you look up and sort of asynchronous libraries in Rust, older ones pretty soon will stop working, or they just won't take advantage of things like async await. But that's all coming soon. So it's a little bit of an influx topic in the Rust community, but it's suffice to say that it's going to be very familiar to anyone who is coming from async await in other languages. And I think some of these concepts like tasks and the executor and its scheduler and how it works is pretty familiar for anyone who is a Go programmer as well. The last thing I want to talk about is kind of the intangibles and sort of the Rust community. So Rust, like Go, is developed in open source. There is a repository for RFCs, which are requests for comment. Basically, this is how the language grows. There is something called the Rust nursery, excuse me. And this is similar to, say, like an Apache incubator type thing. These are experimental projects that may or may not end up being a part of Rust proper. And then there is the Rust Forge, which sort of explains the release. So the stuff that I talked about with features and async await, those are targeting 1.39. So it looks like that's scheduled for November. And eventually, and what happens is when you have these release dates, the stable version will be ticked up to 1.38, beta will be 1.39, and that will be 1.40, for example. I would say as compared to Go, the development process for Rust is somewhat more open. It's not all privy to just the core language team at Mozilla or anything like that. The Rust team posts a lot of their technical video chats with each other, like inside team meetings. They'll post those things on YouTube. I provided a bunch of links to these things, but that was something that somebody asked on Reddit was, what is the sort of the community process like, and how open is it? I would say as compared to Go, it's a little bit more open. It's definitely not a situation where you have sort of these core team members who decide the law, so to speak. And there's pros and cons of that, right? Part of the reason that Go is so successful and it's an awesome language is that it's very simple and very opinionated. You don't see that as much with Rust. There's a lot more community dialogue, and the RFC process is a lot more open to comment. I mean, you'll see RFCs open for several years. So it's a little bit different, but there's a lot of resources that are provided in the repo here. So that's it for my part of the talk. Whatever rest of the time we have, happy to answer any question. Yes?
A little bit more about the motivations for us like I assume not having that one big one safety.
Yeah.
Kind of like talk about those things and compare full borrowing model to reverse counting.
Sure. So, so the question was, what are the motivations for having Rust sort of target traditional systems programming niches like embedded programming or other platforms where you might not want a runtime or might not want a virtual machine? Part of the answer is that Rust is able to not just make syscalls like Go can, but Rust is able to run actually without its own standard library. There's a set of core functionality that will allow you to actually build, say, like a bootloader in Rust. And because of the lack of garbage collection, Rust is able to run in extremely resource-constrained environments. And that's kind of the main reason that it's been seen as, okay, well, if I can run C on this tiny, tiny microcontroller, I can probably also run Rust because there's very little of it. As far as comparing to reference counting in something like Swift, I'm not too familiar with reference counting in Swift, but certainly the RC type that I mentioned in the talk allows you to achieve sort of a heap allocated ownership of several pieces of data, and then you can say, okay, well, whenever the last reference to that thing goes out of scope, then re-edit that. So it's similar, but I can't speak to it because I'm not that familiar with the stress model. All right, well, thank you.